Thank you everyone for coming here today. We from the Antwerp Young Minds in the Department of Antwerp are delighted to welcome this esteemed speaker, Subir Sachdev, to our department to give a colloquium. He first did his PhD at MIT, and afterwards he treaded in the footsteps of Francois Peters and joined Bell Labs, after which he went to Yale, became a professor, and returned to Harvard again, where he's now a researcher. Professor Subir Sachdev is a renowned speaker and got many awards, like the APS Lars Onsager Awards for the achievements in statistical physics. And he also wrote a lot of nice books. One of his nice books is, of course, the quantum phase transition. I got the second edition, and it's a huge achievement to be able to stand on my bookshelf next to all these nice books. Because in this day and age, we only read PDFs, but I always think like you have to buy the book if it's really good. So, yeah, exactly. So this is the reason why I brought it here today. Without further ado, I'll make it short. I can also say that there is afterwards a reception just outside here, where you can talk a bit more with the professor and give your remarks on how good or maybe bad the presentation is. But I think it's only positive. And you can also get a signature in your favorite book if you have it with you. So with all that said, let's give Professor Subir Sachdev a warm welcome to our department. So is the other way. Yeah, okay. Click this on your yeah.
Okay, well, thank you very much. Actually, I don't know your name. You are? Okay. Thank you very much. It's a pleasure to visit here. And Antwerp, thank you for the young minds of organizing this this talk. Okay. Yeah, and thank you for the kind introduction. So I'm going to talk about an old topic, but and I will review a lot of old work, but I will also hope to get to some new ideas and some not so new ideas, and how I think they are finally leading to some kind of understanding of a long-standing problem of superconductivity in the cuprates. So I should mention, first of all, there's a number of collaborators, my students and former postdocs, all of whom are here, noted here. Anyway, so all of this work is done in collaboration with them. Okay, so I'm going to begin with an introduction to, even if you've not seen it before, the phase diagram of the cuprates, and then I'll give, in the first 3 or 4 parts, a very elementary introduction or a set of ideas, well, elementary and not so elementary set of ideas, but using just pictures, using just some qualitative pictures, which I think basically give you the basic, the essential essence of the ideas. And then if I have time in parts 5, 6, and 7, 5 and 6, I'll talk about the recent work, which requires some technicality, but we'll see. I probably won't get to that part anyway. Okay, so this is the basic problem we've been interested in since the discovery of high temperature superconductivity in the cuprates in 1987. So they all have the same basic structure of layers of copper and oxygen. So here I've simplified things even further and just shown the copper atoms that form a square lattice. And typically people take some dispersion of electrons moving on this copper lattice. And then there's a nearest neighbor repulsion, U, and this is an effective Hubbard model. But of course, there are many other terms that are present in the real system, including long-range Coulomb interaction, electron phonons, and of course, no one knows how to account for all of them properly. But many of us believe, including me, that these are the essential terms, the ones I've shown you. Okay, so the one very important number in my discussion will be the density of electrons in this single layer of copper orbital. Because there's only one orbital per copper that's active. So it's just a single band Hubbard model. So the density we say is 1 minus p. That's how people measure it. And they give the value of p, which is called doping. And when the doping is 0, you have 1 electron per site. And that material is an insulator. In fact, it's an antiferromagnet. The spins all form this checkerboard arrangement of up and down spins, and that system is an insulator. So we are interested in what happens when you dope this antiferromagnet. Okay, so here's a phase diagram from a few years ago, and this is going to be a reference to everything I'm going to talk about. So a lot of things are going on as a function of doping and temperature. Of course, the most interesting thing for most people is the superconductivity, which has Tc as high as 100 Kelvin or even higher in some other compounds. And here's the antiferromagnet I already mentioned. This is when P is close to 0, you get the antiferromagnet. And when the antiferromagnetism disappears, eventually it's replaced by superconductivity. But at low temperatures, many other things also happen, depending on which compound you use, depending on whether you apply a magnetic field to suppress the superconductivity or not. You can also get various charge density wave orders appearing. But the focus of my talk mostly will be on what happens above Tc. Now, if you took almost any superconductor, including many of the new ones, and you went above Tc, things become very familiar. You can describe it by Fermi liquid theory, density functional theory. It gives you essentially a complete description of the normal state, if not of the Tc. And here, the dramatic thing is that does not happen at all. And so really the focus of my talk will be to talk about the pseudogap phase, which I'm now going to say a little bit more about. But before I get to the pseudogap, let's talk about what happens at very large doping. So at this point, you do get a familiar state, the Fermi liquid. And one way you can see that is by looking at the Fermi surface. So this is a photoemission observation of the Fermi surface, the locus of zero energy fermionic excitations. And Fermi liquid theory says that the volume enclosed by the Fermi surface, which is this region here, should be equal to the density of electrons. And indeed, that works out. And many other things about the Fermi liquid also work quite reasonably. Okay, so that's good. Now, in the usual approach to different types of ordering in metals, which has been thoroughly established and very, very successful, you start from the Fermi liquid, and then you look at its instabilities. It can have the BCS instability to superconductivity. It can have charge density wave or spin density wave instabilities. Okay, so you could do that even in these materials, but the first thing you notice is that the place the Fermi liquid appears is where nothing interesting is happening. So really the point number one of my talk is we cannot think of these low temperature phases as instabilities of the Fermi liquid. Okay, so what about, let's go to the metal that you see at lower doping, where the Tc is high. So there we have a system metal, which people call a pseudogap. And one of the reasons it's called a pseudogap is if you look at the Fermi surface in photoemission, this is actual photoemission data. I'm sorry, I should have put the reference. Then you see these gaps. There's nothing here. If you compare it to the Fermi liquid, you get a complete arc. But what happens here is that there are no intense low energy excitations in this region of the momentum space once you're in the pseudogap. Okay. So you just get these arcs, and nobody's theory has arcs. So anyway, they're called Fermi arcs just as an experimental summary of what's actually seen. All right, so first of all, to begin anywhere, before we even talk about superconductivity, I think many of us have believed that you need a theory of the pseudogap. You need to understand what the state is. And then, once you understand it, then just like we did for the Fermi liquid, we ask what are the low temperature instabilities. So we need a theory for the onset of charge order and D wave superconductivity from the pseudogap metal. And one of the things you noticed has also been kind of emphasized in this plot by Heimer et al. Is that the instability temperatures of Tc for superconductivity and for the charge density wave are about the same. This, let's see, this Tc is coinciding with this TCDW, and the onset of fluctuations that you can see in different measurements, diamagnetism for superconductivity, X-ray scattering for charge density wave, all roughly happen around the same temperature. And this is, from the point of view of Fermi liquid theory, this is highly surprising. There's no reason at all for these two instabilities to be even roughly the same. They're determined by very different types of interactions, and why should they be the same? Okay. So one popular approach to understanding the pseudogap is that go the other way. Let's start from these ordered phases. Let's not ask where they came from. And then you raise the temperature and have the whole thing fluctuate. And then, so the pseudogap is just a fluctuating phase of some low temperature ordered state. So that's definitely not a point of view I'm going to advocate. I mean, many people have worked on that a lot. And we could go into the details why I don't think that's the right way to do it. But the basic point is that, these temperatures, 200, 300 Kelvin, are still very low temperatures compared to the natural energy scale, which is, almost 2000 Kelvin. And so the point of view is that the pseudogap, just like the Fermi liquid, is a phase that is a quantum phase. It's not fluctuating of something else. It's a phase in its own right, which in principle could exist at zero temperature. Now, it doesn't exist in this material at zero temperature. Well, neither does the Fermi liquid. Almost any metal, if you close it, go to low enough temperature, is a superconductor, or something happens. So these phases are intrinsically have some very low temperature instabilities, or perhaps in this case not so low temperature. But they still should be thought of on their own right as their own quantum phases, not the fluctuating of something else. Okay, well, anyway. So that's what I'm going to present. So first step one will be to present a theory for the pseudogap metal. And then we do the next step, and this is still work in progress. Once you think you have a good theory of the pseudogap metal, let's think about what are its instabilities. Just like we know about instabilities of the Fermi liquid, what are the instabilities of this new type of metal? All right. So let me tell you one thing about the theory of the pseudogap metal, which is actually a feature of many other works that I've cited here over the years. So our claim is that these Fermi arcs are really a remnant of actual pockets. There are actually whole pockets here with a backside. It's just that the intensity of photo emission is very weak at the back. So they're really pockets of size p, and these are pockets of just ordinary electrons, charge e, spin a half quasi-particles. Okay, and this is a feature of many other works. But one of the things we're going to emphasize, and really the key to special features of our work, is that once you have such pockets, then you've done something really that's not allowed by the usual principles of condensed matter physics. So before I get to that. So there is some evidence that there is actually a backside here. And this came from angle-dependent magnetoresistance measurements. Okay, so I can discuss this in private for those of you who want to know how these measurements are done. And there is some, indirect but pretty good evidence for there actually being pockets. So this theory has some support in that direction. Okay, so what I was starting to say earlier, once you have whole Fermi surfaces of size p, you have then done something that's not allowed by the principles of everything we learn in condensed matter physics in the textbooks, you violated the fundamental theorem, which is the Luttinger liquid. And Luttinger theorem, which is that the Fermi volume enclosed by the Fermi surface should be the density of electrons, modulo 2. So here the density of electrons 1 minus p, or in terms of holes, that 1 plus p, but you've got now hole pockets of size p. So you're missing 1 electron or 1 hole per unit cell inside the Fermi surface. All right, so there is a state of matter that we proposed many years ago, sometimes called FL star, which says you can't, such a state of matter is allowed. But it's only allowed if you have, in addition to these hole pockets, you have another sector of the Hilbert space, which is a spin liquid. Okay, so you can't get hole pockets on their own. You can only get hole pockets of the wrong volume, provided there's a spin liquid around. And this spin liquid will play a crucial role in this low temperature instability. So this is the summary of my talk, if I don't get to it. So the onset of conventional order, meaning order to superconductivity or charge density wave or spin density wave, is a confinement transition of an emergent gauge theory. You have to use an emergent gauge theory to describe the spin liquid. And the spin liquid has some fractionalized excitations, the analog of quarks in quantum chromodynamics. And these quarks, in this case, will move under, I claim, an SU2 gauge field, not an SU3 gauge field. And so you need the full theory of these quarks and the gauge fields, and to have a theory of the metal, and then to have a theory of the onset of TC. And we're a long way from making this quantitative, but I'm going to argue that there's a lot of experimental and numerical evidence supporting this basic picture. Okay. All right, so that's kind of, I gave you the experimental puzzle, some of them, there's many others, and at least the claim, and I'm now going to give you just by drawing pictures, I'm going to explain these ideas, just by drawing some very simple pictures, okay? And then toward the end, we can go into complicated field theories if there's interest. All right, so the first thing is all these mysterious things I've just talked about, if you haven't seen them before, is to do a theory of quantum spin liquids and this state of matter we call Fermi liquid star. I mean, this is supposed to mean that it's a Fermi liquid in the sense that it has ordinary quasi-particles, but it's a star because it's violating the Luttinger theorem. It's an asterisk, which is actually the key to everything. All right, so let me just start with what is a quantum spin liquid. So, as I mentioned earlier, when you're at p equals 0 with 1 electron per site, the system forms an antiferromagnet. And this is due to the exchange interaction between the spins, which is antiferromagnetic in the Hubbard model. And so you get this checkerboard structure, which is well understood and studied in experiments. So, however, this long-range order, so this is long-range spin order, disappears fairly quickly, and it's certainly not present in the pseudogap, at least in the whole loop cuprates. There's not even any appreciable spin correlation length. So we don't want to start from this state. So it was proposed, by Anderson, like literally months after the discovery of ITC, that the correct state to start with is a spin liquid. So the spin liquid was hypothesized by Anderson way back in 1973, and there was no work on it until 1987. And then, of course, there was an explosion of work. Luckily, this is when, I just started my first job, and I said, I'm going to work on spin liquids. And it was a very exciting time with a lot of discoveries. But it's taken 25 years to really it's rather complicated subject, but I think today we can say we have a pretty good understanding of what spin liquids are. Even though experimentally they're still not as well understood, theoretically with numerical work and a lot of input from mathematicians and particle physics, we have a very good understanding of what spin liquids are about. So let me just give you some pictures. So in Anderson's picture already in 1973, he had the picture that the spins, of course, if you just had a pair of spins, they like to form a singlet, up, down, minus, down, up. That will optimize the exchange interaction between them. So in this configuration, I paired the spin up in some way so that you optimize the exchange interaction on some of the bonds, but not all. So what about the other bonds that are now not taken advantage of? Well, you can take advantage of the bond by actually a process that was already known in chemistry called resonance, where you have resonating bonds in the structure of benzene. So here you do resonance not on just one hexagon, but in the entire square lattice. So there's really an exponentially large number of configurations, and the actual wave function is the sum of all of these singlets. Okay, so that's point. It's statement 0 about a spin liquid. It's a state that has, today we would say the state has long range entanglement, because in some very sense that can be made very precise, electrons on this side are entangled with the other one because this resonance entangles them all together. So they're all entangled. All right. So now I haven't told you the relative phase factor between all of these singlet pairings. Can you get singlet pairings between further neighbor bonds, and so on? So none of this was understood. Today it's extremely well understood, and we have a very precise language for talking about all of this. But let me continue. So that's a rather bizarre state. Well, what about its excitations? So I'm not sure exactly when this was pointed out, but I think perhaps Anderson already knew this. I don't know, but certainly Kivelson was important in emphasizing this in the early days. So let's take an excitation. So one thing you could do is you could take the singlet bond and you break it. And now you have a remarkable feature that these objects can move apart out to infinity. And that object that's moving out carries spin 1/2 and charge 0. Okay, so it's an excitation which has half integer charge, half integer spin, but 0 charge. And such a thing, is not allowed in anywhere in Fermi liquid theory, BCS theory, magnetism theory. The conventional theory always has every time you have a half integer spin, you have a one charge, odd integer charge. Every time you have an 0 spin, you have to have even charge. You cannot have anything like this. So this is an emergent particle that doesn't exist in any system, that any state you would get by perturbation theory from a Fermi liquid. Okay. So this is an excitation that, by definition, exists in a spin liquid. In fact, this is a better definition of a spin liquid than the other definition, where I just say it's resonating valence bond. That's a rather vague thing. This is a very precise statement. It has an excitation which has unconventional quantum numbers, where the spin is in half integer, but the charge is 0. I mean, spin waves and paramagnons, they all have integer spin. They don't, even though they're charged 0. Okay. Now if you now dope the system, now you come up with another possibility for exotic excitation, these vacancies. These vacancies can now move around in the background of the resonating singlets. And so these vacancies now, I guess I haven't shown them moving around. There's moving. So these vacancies have carry charge E and spin 0. So what's happened, roughly speaking, the electron, which has charge E and spin 1/2, has fractionalized, has split into two different particles. One has the charge and the other has the spin, hence the word spin charge separation. Okay, and now, you're getting somewhere. So now if you imagine these vacancies, which are called holons, were fermions, and in some theories they can be fermions, then they'll form a Fermi surface if they are approximately free fermions, these on the background of this RV resonating valence bonds. Uh, so they form a Fermi surface, you get a metal. And so one of the earliest ideas was, well, this could be an explanation for the pseudogap. That you've got this metal of these holons moving around, and they're either forming a Fermi surface or they're somehow incoherent and giving you these arcs, and that should explain the pseudogap. But quickly we realize it, well, not so quickly perhaps, it cannot work. And the reason it cannot work, because the photo emission experiments, which showed you the arcs, those are experiments which eject an electron. So when you eject an electron from the system, you're creating an holon, but you're also creating a spin-on because the ejected electron carries spin. And the spin-ons, are excited state. They have a gap. They're not zero energy states. So you wouldn't get a Fermi surface because you have to pay the energy for creating the spin-ons. All right, so how do you fix this? Well, so this is where the FF star comes in. So in this state, you've got an exotic state. In principle could exist where you have a Fermi surface of size p, not 1 minus or 1 plus p. But it doesn't fit the observations. So the state we proposed was the following. So let's suppose you have a whole bunch of holons. Those were there because you doped the system. And now you create some spin-ons. Now the spin-ons, that's going to cost you some energy. So why should you bother to create them? Well, what could happen, these spin-ons could move around, and they could each bind to a holon like that. And then that's going to gain some energy because there's some binding in it. Suppose they're strongly attractive. In fact, there is a strong attraction between them. So suppose they form a bound state. So then you'd be willing to pay the price to create a spin-on because you'd gain energy from forming the bound state with the holon. So you will get this state here, where now I've taken the spin-on and the holon and have them form the green dimer, which is just a word for an electron hopping on a bonding orbital. And then I still have the resonating valence bonds. Okay. So now this is our proposed state for the pseudogap, and I believe it fits all the criteria. So first of all, these green objects are fermions, and they have to be in anybody's theory because they don't have fractional quantum numbers. And so they can form a Fermi surface. And furthermore, the density of these green objects is p. It's not 1 minus p or 1 plus p. So they will form a small Fermi surface. Okay. So you've got what you needed. You violated Luttinger's theorem. You've got a small Fermi surface. But you had to pay a price. You can't just do this in a vacuum. You pay the price, you still have the spin liquid sitting around. Okay, if you looked at this picture in a colorblind way, oops, there we go. It just looks like the original spin liquid of Anderson. It's just the same resonating dimers, except some of the dimers have been replaced by electrons. That's all. That's just a very simple, crude picture. So the spin liquid is there, and it has consequences, and have experimental consequences, and we believe also, consequences for the onset of superconductivity and so on. In particular, you can now also imagine that these green objects can pair. So I put them next to each other, and now they can move around. And as they're moving around, since they're now bosons, this paired object, that will give you superconductivity. All right. So that's it. So those are the very simple ideas presented in cartoon pictures. Of how you get the pseudogap metal, and how from the pseudogap metal these pre-existing dimers could condense to form a superconductor. And the rest of I've gotten through that fairly quickly. About halfway through. And the rest is now, how do you make a real theory about this? These are cartoon pictures are fine. You can do a few cartoon calculations, which we've done. Now the time, 30 years later, it's time to do a real calculation. We're not there yet, but really sharpen this and make this a real theory. Okay. But anyway, this is a good point to pause. Are there any questions on just these pictures? Okay, so everyone, yes.
So the temperature is lower in the gap for the
Yes, yes. I mean, okay. As we'll see, the spin-ons can be gapless, but it's certainly lower than J. So it's low enough that these valence bonds will want to form. There may be some spin-ons also around because they may not.
to lower the energy of the
Yes, exactly. Yeah, yeah. That is, you're willing to pay the price, provided the binding energy of the spin-on and the hole-on is large enough, like there. In fact, the binding energy of this is P, which is much bigger than J. So in fact, it is the largest energy in the problem. Well, compared to U, of course, U is infinity, but this binding energy is the hopping matrix element. It's very large, and I don't know. We proposed this state in 2004. It's kind of embarrassing because people overlook this very simple effect. Anyway, um, yeah. So that's really the picture that there's a spin liquid, and from the spin liquid you can get this exotic metal that violates the Luttinger theorem. So it has the Fermi surface of the wrong size. And then as you lower the temperature, if this was the right type of spin liquid, it would be present all the way down to zero temperature. So now today we understand which spin liquids are stable and which are not stable. And the reason that's not an obvious question is once you form a spin liquid, then there's always some emergent gauge field. There's long range forces that appear. And those can lead to confinement. We know QCD always confines the quarks. So similarly, there are similar questions here, which are actually in many ways much harder because you're dealing with system where a finite density of fractionalized particles. So then it becomes a question of how stable is your spin liquid? And if it's not stable, then how does it undergo an instability? And these are questions we know how to answer extremely well for Fermi liquids, and we are working on how to answer them for such spin liquids. All right, so to get to some actual theory, I want to actually review very quickly some basic fact about a state of matter called the heavy Fermi liquid, which is widely seen in many materials, these so-called heavy fermion materials. So there's materials like cerium, cerium copper 6 probably is probably one of the most famous. So these are materials with some rare earth element and some ordinary metals, which combine to give you metals which have quasi-particle electronic masses, which are 1,000 times the bare electron mass. And these are all understood in the context of what's called the Kondo lattice Hamiltonian. So what is the Kondo lattice? So this is just some background I will need to make up my theory of the cuprates. The theory of heavy fermion compounds is much farther advanced. I think we have a pretty good understanding of what's going on. Because in the end, when the dust settles, these systems are Fermi liquids. Those are much easier to understand. Okay, so what describes the Kondo lattice or these heavy fermion compounds are the following type of model. So this is the Kondo lattice model. So you have two types of elements in these heavy fermion compounds. There are the rare earths like cerium, and in this, let's imagine that the rare earths on a triangular lattice with one spin and a half on each side. Okay, they can be more complicated, but anyway. So these are F electrons. So these are the F band, and they're forming some kind of antiferromagnet. And then there's some conduction electrons, the C electrons that come from copper or whatever, some more traditional metal, and they would form a Fermi surface on their own. So the total number of electrons in a simple picture is you have, say, electrons of density p from the c electrons. And now these are exactly 1 electron per site, so density 1 of f electrons. The total density is 1 plus p. Okay. And then these are coupled together in the heavy fermion compounds. And the coupling is right here. It's called Kondo coupling. Each F spin has an exchange coupling to the conduction electron on that site. And this is the J Kondo exchange, which is positive. It's antiferromagnetic. Okay. So basically, each localized F spin wants to take a conduction electron and form a singlet with it. But the conduction electrons are moving around. Okay, so now the case where there's only one F spin and some conduction electron is the original Kondo impurity problem that's been thoroughly studied and understood. This is the Kondo lattice extension. This has also been thoroughly studied and pretty well understood. And what we know experimentally and what you can also get from a treatment of the Kondo lattice is you get a metallic state, which is just a Fermi liquid. Okay. So then what should be the volume enclosed by the Fermi surface? Well, the volume enclosed by the Fermi surface by Luttinger's theorem should be 1 plus p. And that is exactly what you get. You get a big, what's called a large Fermi surface, and the volume enclosed by it is 1 plus p. So in other words, so in some sense, there's something rather remarkable has happened. These F electrons, these are spins, they don't actually move in this Hamiltonian. In the Kondo Hamiltonian, they're just sitting there forever. They're just some qubits. Each of the spins could be replaced by a superconducting qubit, or your favorite qubit in your quantum center. It's just two level systems. They're not actually moving. They're really bosons in a sense. Nevertheless, when they Kondo exchange with the conduction electron, they become fermions, and they become part of the Fermi surface. But because these don't move at all, they're infinitely heavy. So there's what people say is an hybridization. They hybridize with the conduction electron, and they hitch a ride on the conduction electrons and effectively start moving. But because they were initially stationary, the mass of the quasi-particles, so you get this Fermi surface which is large, but the mass of the quasi-particles is extremely large. It could be 1,000 times the mass of a bare electron. All right, so that's a quick summary of the theory of heavy fermions, which there's a book, I think, by Hewson, which goes into this theory, including connections to experiments. And, it's really an important achievement in condensed matter theory, where we have, it's not as quantitatively accurate as identifunctional theory, but it's getting there. It's really well describing a whole bunch of experiments in a rather non-trivial state of matter. It's unfortunate that the state of matter is just a Fermi liquid, depending on your point of view, but it's a very bizarre Fermi liquid, which is called the heavy Fermi liquid phase. And what's bizarre about it is that these F electrons effectively become mobile, even though initially they're just F electron spins. Okay. All right. So I'm not talking. So the thing about the cuprates is I can't just apply this theory because there is no Kondo lattice in the cuprates. Every experiment has shown just one band near the Fermi surface. It's okay. There's copper and oxygen, but when you do the band structure, the oxygen bands are way off. They're not active at all. So it's a one-band model. It doesn't have a Kondo lattice description. So I can't use the Kondo lattice to start thinking about the cuprates. All right. Okay. Everyone with me? All right. So now let me give you a more sophisticated theory of this FL star state. And so now what I want to do is violate the Luttinger theorem in a single band model. Before, actually, I should say, it's actually quite easy to violate the Luttinger theorem in this system. Suppose I turn down the Kondo exchange constant. So what can happen is that these F electrons can form a spin liquid. And then the C electrons would form a Fermi surface, and you get a small Fermi surface, but there'll be a spin liquid hanging around. So that's originally the way we thought of the FL star state. I should have made a transparency of that here. But now the question is, can you get the FL star state without in a single band model, in just a Hubbard model? Okay. So that's the heart of the whole calculation that I want to now describe. So this happened a few years back in the pandemic. All right. So here's how you might get a real theory for this FL star state, which allows you to actually compute things. So let's start with our favorite Hubbard model again, which I started the presentation with. And then you do what's called the Hubbard-Stranovic transformation, extremely common in all branches of solid-state physics. In this case, for example, I take the Hubbard interaction and I write it as the square of the local spin operator plus some constant. Then I could rewrite this interaction as spin square. And then this is the Hubbard-Stranovic transformation. I just when I integrate over phi, I would get spin squared. This is the spin operator here of the electrons. So basically, I can replace the Hubbard interaction by the fermions interacting with this field phi. Okay. And this phi is basically some version of what's called the paramagnon. So there is some collective spin 1 excitation that could be present and seen in metals which are close to some kind of magnetic transition. So helium-3, the favorite theory of superconductivity in helium-3 is paramagnon exchange. That can be ferromagnetic or antiferromagnetic depending on the details. So the only point of this transparency is to argue that you can exactly rewrite the Hubbard model as a theory of free electrons interacting with a spin 1 boson. Okay, that's just a naive transformation. But and the important point is spin 1. It's not a spin on, which would be spin a half. Spin 1. It's integer spin. Okay. So let me draw that in pictures. So here's the Hubbard model. So this is supposed to be a square lattice. You should just think of it. I'm looking at it edge on. So here's the Hubbard model that I'm interested in. I just showed you that you can rewrite the Hubbard model as two electrons interacting with a spin 1 boson. Okay, so I'm going to do that here. I'm going to claim that the original Hubbard model is equivalent to 3 electrons on the top layer. Each of these are square lattices looking edge on, and 2 layers of spins coupled with a mutual exchange J perp. So now imagine J perp is bigger than anything else, then the spins will just form singlets. Okay. But what are the excitations of these extra layers or ancillar layers? And there's an excitation which is this triplet, and this can move around, and that's my paramagnon. So I claim is that I can rewrite the Hubbard model as this 3-layer model where the bottom layer has a spin 1 paramagnon, bottom 2 layers, and the top layer is coupled to the physical layer by antiferromagnetic exchange coupling J condo. Okay, so my claim is I can rewrite the single band Hubbard model as some kind of condo model, but not with 1 layer of spins, but 2 layers of spins. And they have to be spins that can form a trivial ground state, which they can form the singlet state, but then the top layer would just form a Fermi liquid of the whole density P. And in fact, you don't have to take my word for it. You can do what's called a Schrieffer-Wolff transformation. You can start with this Hamiltonian written here. This is the full Hamiltonian. 3 electrons in the top layer, condo exchange between the top layer and the second layer, and J perp between the first and the bottom 2 layers, the ancillar layers. Now, when J perp is large, you can do a Schrieffer-Wolff transformation. You can eliminate the triplet excitations from here, which is the same as integrating out the phi, and you get back a Hubbard model with U is of order this number. Okay, so I'm just rewriting the Hubbard model as a 3-layer model by this inverse Schrieffer-Wolff transformation. Everyone, this is a proven statement at this point, at least for large J-perp. Has to be bigger than everything else, GK and T and even U. Yeah. Okay, but I'm now going to make J-perp small to get, now if J-perp is really very large, then these spins will form singlet and end of story, I'm back to a Fermi liquid on the top. Okay. So why should J-perp become less important? Well, J-perp could become less important because of what's called the Kondo effect. So if I take a single impurity spin and couple it to a conduction electrons, what Wilson and everybody taught us about the Kondo effect is that J Kondo flows to strong coupling. Under renormalization, it goes to infinity. Okay? And this is the RJ flow for a single spin Kondo effect. If it's positive, it flows to infinity. If it's negative, it flows to 0. There's a fixed point at J K equals 0. And so we assume we're here and it's going off to infinity. So it could happen that under the right circumstances, at long distances, we should really think of JK becoming bigger than J-perp. Microscopically, it's not, but when I do the many body physics and include the Kondo RG, that's a reasonable possibility. Okay. So that's really, in the end, the only unproven assumption. Once you make that assumption, you get, you see, I'll show you, get exactly what you want. So when JK is small, then these two spins will form a singlet, and this will form a Fermi surface of size 1 plus p, which is what you see at large doping. Okay, what happens when JK becomes larger? Which, let's say, what happens when doping is smaller? Well, then, what's going to happen? The top two layers are just like the Kondo lattice I told you about. And what did I tell you the Kondo lattice we now understand likes to do? The Kondo lattice likes to do is form what I call a large Fermi surface, which counts both the spins and the electrons. F plus C went inside the Kondo lattice. So how many spins do I have? The top layer, I have one spin per site. How many holes do I'm thinking in terms of holes? I have 1 plus P. So the total volume of the large Fermi surface is 1 plus P plus 1, which is 2 plus P. But remember, Luttinger's theorem says the volume of the Fermi surface is always modulo 2. Because you can always take 2 electrons, put them in a fill band, and remove them from the Fermi surface. So modulo 2, this is P. So in fact, I have here the heavy Fermi liquid state has a small Fermi surface. It has size P, which is what's seen. And however, we had to pay a price to change the size of the Fermi surface. Like all the pictures I've shown you suggested we will. We have a spin liquid sitting here. So there'll be a spin liquid sitting here and resonating around, and that's also there. Although experimentally it hasn't been directly seen, the claim is that it's there. You just have to look for it carefully and you will eventually see it. Let's see. Okay. All right, so that's our proposal, for what the state is, the pseudogap state is. It's this state over here. And here's the slogan, if you remember anything from my talk. Pseudogap is just like the Kondo lattice heavy Fermi liquid that you get in the heavy fermion compounds. What has accompanying it is a spectator, or maybe not so much of a spectator, spin liquid. So in the Kondo lattice, you don't have this part. If you had an ordinary Kondo lattice of just the top two layers, there is no spin liquid. So this is a much more exotic state, which we think is there in the cuprates. Okay. Yeah. Well, neutron scattering at higher energies and finite doping, which should show you the spin-on continuum. There is actually a lot of evidence for such a thing. It just hasn't been quantitatively analyzed. Yeah. That would be the most direct. there is a huge continuum of excitations observed in the neutron scattering. Okay. All right. So in fact, through this, we have done, so these are actual calculations in these papers. Where this is experimental data, these are our calculations. And then we can fit in the using that information, we can really describe details of the photo emission spectrum, both in the nodal and the antinodal regions. These are some data, and these are data, and these are our calculations, and it just works extremely well. Okay. All right. So I have 10 minutes left. Okay. So at least I've hopefully given you a picture and maybe even some, some methods of calculating what this state is. The pseudogap metal state, we believe, is this FL star state, which has a spectator spin liquid. And to explain the photo emission experiments, I could just ignore this spin liquid. It didn't matter. But now, what the remaining task is to now lower the temperature and ask how this state goes into superconductivity, charge density wave, and all the other things you see. And there we claim is you cannot ignore it. You have to, the spectator becomes not just a spectator. It's the physics of the spin liquid that's driving the onset of superconductivity in particular. Okay. So if you're going to address that, then the question becomes which spin liquid? Okay. Now this question didn't even have some meaning in the early days of cuprates because there was no classification of spin liquid. Today there is a classification. I mean, it's not complete, but it's getting there. We know exactly how to characterize spin liquids. As the gap, they're fully characterized by topological quantum field theory, plus some additional symmetry constraints. So it's called symmetry in niche topological order. So there's a very fancy and rigorous mathematical theory of gapped spin liquids. For spin liquids that don't have a gap, there is no such rigorous theory, but again, a lot of progress. And in fact, what I claim we will need is a spin liquid that does not have a gap. Okay, so this is where things are going to start getting a little technical. I do have to use some new types of formalism. So, okay, but there's only 10 minutes, so let me quickly go through it, or even 5 minutes or something. Okay. And this is a belated realization. I mean, for a big part of my career, well, I would, 10 years ago when I started thinking about such ideas, I was really holding out hope this would be a spin liquid that could be seen at 0 temperature. You'd like to see something. If you think of a new phase of matter, you want it to be stable, right? So that's what I wanted for the longest time. I mean, now it's pretty clear that there's no sign of such a thing at low temperatures in any cuprate. When you go down to very low temperatures, they always, either they have a charge density wave order or they are superconductors or they are stripes or something like that. And there's no spin liquid. All right, so you can either give up, about spin liquids, but like I said, there's no other way to understand the pseudogap in my mind than a spin liquid picture. I'm not aware of any theory that can explain the data as well as we can. So spin liquids are definitely needed at a pseudogap. So then how do you put this together? Well, maybe there are some nice spin liquids that have just the right feature that they're unstable at strong enough distances. Okay. And strangely enough, I had been working on a spin liquid for quite a long time. Okay, and that's called the pi-flux spin liquid. So there are many other words. So let me know. So with apologies, I'm going to move fast and just give you some flavor of how these theory of spin liquids work, and how you would write down something to describe the confinement of such a spin liquid into superconductivity and charge density wave. So one of the things that comes out of our theory is that, in fact, you get D-wave superconductivity, not any other. D-wave is a feature of the superconductivity that you get. All right, so one of the earliest theories of a spin liquid was by Arovas and Auerbach, where they took the square lattice antiferromagnet and rewrote the spins in terms of these bosons. So these are bosons, there's one boson per site. It can either have spin up or spin down. And this is the spin operator in terms of these bosons. So you get a Hamiltonian that has only 4 boson term. And the Hamiltonian also has a gauge symmetry because you can rotate the phase of any boson on any site. Since the boson cannot hop, it can only exchange spin. The number of bosons on each side is conserved. And associated with that is a U1 gauge symmetry. So the low energy theory of these bosons will be a U1 gauge theory, like electromagnetism, but also something that's what's called compact, so it has monopoles, and that's actually crucial to the whole story. Anyway, under the right circumstances, when you do a mean field theory of the bosons, you can get some state after you do a mean field theory, you do some Bogoliubov transformations, and you get a mean field state, which seems to preserve all symmetries. So that's a spin liquid, and it has some gapped spin-ons, which are the bosons. All right, so this is what Orovitz and Auerbach proposed in 1988. But soon after, we showed that their state is unstable. It's unstable because of these gauge field and the monopoles, and they lead to this valence bond solid order. Okay, but there was this critical point here where there could in potential be a very large length scale, and now there's a lot of numerical evidence for that, where this spin liquid is kind of stable up to some large length scale. At this point, it wasn't clear whether at this critical point the spin liquid is stable or not, but through a lot of numerical work in the last 20 years, we now know it is unstable, but only at rather large length scales. So that's perfect for our purposes, actually. All right, so this was the first description of the spin liquid in terms of these bosons and this critical point between the two conventional state with a gauge theory describing the transition between them. But also in 88, there was another approach by Affleck and Marston, who said, let's decompose the spins into fermions. These are the fermionic spin-ons as opposed to bosonic spin-ons. And so this turned out to be an SU2 gauge theory, not a U1 gauge theory for complicated reasons. And the fermions, after you do some Hubbard-Tratanovich mean field theory, were moving in pi-flux. So this is a picture of fermions in pi-flux. And now, if you just diagonalize nearest neighbor hopping on the square lattice with pi-flux, you will get a Dirac spectrum. So this is just like if you take electrons on the honeycomb lattice, you get 2 Dirac points. If you do that on the square lattice, you don't. But if you put pi-flux in each plaquette, you get 2 Dirac points. So the system here generates some internal gauge flux, which gives you these Dirac points. So that's also a spin liquid proposed by Affleck and Marston, and it looked completely different from Orovitz and Auerbach's spin liquid because this had bosonic spin-ons. So Orovitz and Auerbach had bosonic spin-ons, this has fermionic spin-ons, and these spin-ons are gapless. Those spin-ons were gapped, just looked like something different. And for the longest time, there was a battle on who was better. Today we know they're the same. So that's one of the amazing things that's been learned in the last 5-6 years. That if you take this theory of Affleck and Marston and put in all the gauge fluctuations completely, well, it turns out to be an SU2 gauge field. And a lot has been learned about this SU2 gauge theory. This is and all its instabilities. And in the end, you get the same phase diagram that we had proposed using bosonic spin-ons. There are 2 possible confining phases, the Néel state or the valence bond solid state. And there's an intermediate region where the things are very low energy, where this critical spin liquid could survive. Okay. And there's some numerical evidence supporting this picture in terms of the spectrum. So in fact, this is some numerical data of this transition in quantum Monte Carlo. And this is just comparison with 3 fermions moving in pi-flux. That does a beautiful job. And this is, you take a more realistic model, J1 and J2 exchange interactions, and you indeed find Néel order and valence bond solid order in some intermediate window of spin liquid, gapless spin liquid type behavior with Dirac spectrum of spin-ons. And finally, this is, I guess I'm out of time. So let me also mention this very beautiful recent study by Hongchen Jiang and Steve Kivelson. So what they did here, they take the J1, J2 model, this model right here, which has this phase diagram. It goes from an antiferromagnet to a valence bond solid with a spin liquid in between, and then you dope it. Now, people have been doping antiferromagnets and for decades and studying them, and in fact, it's been very hard to find robust high temperature superconductivity. It seems to compete with charge density wave order, and they're all kind of marginal. But in this case, they show numerically very recent work. It's very robust D-wave superconductivity. So this particular spin liquid, that's been my favorite spin liquid for 20 plus years, is exactly what you need to get, in fact, high temperature D-wave superconductivity. This is some numerical evidence by Kivelson and his collaborators. All right, so finally, I think I'm out of time, but so now we have to put all this together. I have a theory of the pi-flux spin liquid, and then I have to now confine it at finite doping in the FL star state. And well, anyway, so how do I do it? You start with the pi-flux, then you put in some charged boson, which you argue must also have pi-flux. Then you look at the instabilities of these boson. These are Higgs fields, so there's a fundamental Higgs field. It has various flavors, and in fact, its condensate have exactly the right type of order. It has stripe order. It has D-wave superconductivity, and you get some beautiful phase diagram that we're still working on. All right. So to conclude, let me just recap. So to recap, all this richness is in this very simple model, which that even today is not that well understood, but it's probably responsible for high TC superconductivity. And underlying the physics of the cuprates, we propose is this kind of quantum phase transition. There are two different types of metals. And there's the familiar metal, which is FL, and there's a novel metal, which we call FL star. And this FL star can be thought of as roughly the sum of a Kondo lattice heavy Fermi liquid and a spin liquid. And then when you confine the spin liquid through various methods, you get everything that's seen. So this is the part the more recent work. You start from this pseudogap metal. When you go across the quantum critical point to the Fermi liquid, you get a strange metal behavior. If you confine it with these Higgs fields, you get D-wave superconductivity and charge order. This all comes out. This is not something that's put in by hand. Or you condense the bosonic spin-ons, you get pi-pi and Néel order. And I'll leave it at that. Thank you very much.
We still have time for some questions.
Yeah.
So there's also same experiment with the finger, except of course now
yeah.
smoking and gun.
Well, so one would certainly be, an experiment that, the analog of this numerical work on the frustrated antiferromagnet, like this. So this kind of data does exist to some extent in the cuprates. So if you can really do a careful theory of the spin liquid of the FL star and compare it to experiment, that would be now. But there's many things that are explained by this theory. One of being the photo emission data that I showed you. It's hard to think of experiments that haven't been done. That's the trouble with an old field. Almost everything's been done, and I claim that I'm not aware of any existing experiment that, at least in principle, wouldn't fit to these pictures. That's my. I don't normally make such big claims, but I think I'm starting to feel comfortable with such a claim. Yeah, what smoking gun experiments? Well, yeah, that's so. Well, right now we're trying to do some quantitative theory of this in terms of a gauge theory of how you get fluctuating charge order and superconductivity around the same scale. Let's see how that works. There's another open problem which I haven't mentioned is in this charge density wave state, there's these quantum oscillations with electron-like pockets. That can also, we believe, be explained in this type of approach, but we're still trying to make it quantitative. Yeah, there's a lot of stuff on the strange metal, but I didn't talk about. There are also, yeah, okay. But I don't. I think I'm forgetting something. There was one other smoking gun we had in mind, but anyway. Yeah. Yeah. Anyway.
Before the predict on the recipe for it.
Yeah. Right. Well, other than saying the doped spin liquids are good, I mean, it also has to be this type of spin liquid. So somehow I don't think triangular lattices will work. Square lattice somehow seems to be exactly the right thing. Yeah. So, if you take a square lattice and then maybe frustrate it a little bit, for example, what came out of this study here is that when you're down here, the physical value of J2 in the cuprates, whoops. Yeah, the physical value of J2 in the cuprates is 0.1 or something. And when you do numerical studies on 0.1, down here, now there's starting to be evidence for D-wave superconductivity, but it's rather delicate. It's, about 100 Kelvin is still a very low temperature on the scale of these theories. When it's very delicate with charge density wave order. So when you actually start with a spin liquid rather than an antiferromagnet, it's really robust. So, yeah, I mean, I would say there you go. If you could get a square lattice system where J2 is around half of J1, you'd be in business. You want second neighbor exchange to be a little bit larger. Yeah, that's what I would say. Yeah.
Yes, I'm not sure when it's
Yeah. So right. So you take this antiferromagnet, and then you write each spin operator in terms of these fermions. So you get some Hamiltonian for the fermions, which have 4 fermion operators. You just approximate it by a mean field Slater determinant. Okay. So we just do the simplest possible thing. You have some interacting fermion Hamiltonian. We do what we always do. Assume a Slater determinant is the ground state and then optimize it. Yeah, I'm coming to that. So the difference from this problem from other problems is that these fermions do not have any dispersion. Okay, so normally if I'm doing some density functional theory, I take in my interactions and then you normalize some bare dispersion, I get a new dispersion, and then I just take, okay. Here there is no dispersion, so I'm free to take any dispersion I want. So it turns out the dispersion that works best is this dispersion shown here, where the green bonds are -1 and the red bonds are +1. So now if you look at the flux through every plaquette, it's -1. So that's the pi-flux state. And pi is special because it doesn't break time reversal. So you want a spin liquid state that preserves time reversal, and pi is the case. Now it could have been 0, it could have been 0 flux. That wouldn't have given you Dirac fermions or given you a Fermi surface. But that's not the one. To get all the physics we're describing, the pi flux is actually crucial. Yeah. So what is this flux in? And the question is, as I said, these fermions carry an emergent gauge charge, which is the U1 symmetry associated with local constraint. So this is not a physical flux that you would impose by a magnetic field. It is a flux in an internal gauge field. This emergent gauge field that can carry flux, and the mean field state has pi-flux.
And before moving on to the reception, there is one last critical part, which is that we have the tradition, it seems, to not only give our speakers a warm welcome, but also a sweet welcome.
Oh, thank you so much.
Some Belgian chocolates, of course, and because we are
Very
super
kind.
patriotic, also some Antwerp hands.
Oh, very nice. Thank you. I've never heard of these ends. Okay. Thank you so much. Okay. Thank you. Beautiful.
Thank our speaker again for
Okay.